Hey guys, my name is Theo. I'm chief architect at a Swedish startup called Burt. We're in the business intelligence sector for publishers and media owners. So we do like analytics and other kinds of things for publishers to help them understand what their revenues are and how they work and their audiences and that kind of thing. But I'm here because I like Ruby and I like Cassandra. But they haven't really been the best of friends historically. There's been Ruby drivers, but they've obviously been based on the Thrift APIs. They have been very low level, very close to the Thrift API, not like the Java drivers that are sort of built on top of the Thrift APIs and made something more usable on top of it. So it's never really been a pleasant experience being a Ruby driver and a Cassandra user. We're a JRuby shop, so we solved that problem by wrapping the Java drivers. So we had a wrapper for Hector and for Astyanax, and that kind of worked. But those are also very Java-centric drivers, even though they were great for Java developers. Putting a Ruby shell on top of them worked kind of, but weren't perfect. So when in January, when Cassandra 1.2 came out with the new binary protocol, also called the CQL binary protocol, or just the CQL protocol. It's got many names. Also, obviously, it's not the native protocol. So that came out in January, and I was really excited because this felt like sort of a great time to make that connection between Ruby and Cassandra work much better. The CQL feels like it's more language agnostic. It's not a Java. It's not Java oriented like the old Thrift APIs. And it feels like this could actually be something. So I'd never written a database driver before. I'm not a database driver expert. I'm not a database expert even. I build big data systems, processing data, and that kind of thing in Ruby. So, well, you know, I'm not really an expert at this, but how hard can it be? And I had I felt intimidated just by the thought of opening a socket, pushing a few bytes down it and see what happened. It felt like, well, you need to know what you're doing to do that. But I sat down with the CQL protocol specification and the Ruby sockets API documentation and figured, well, I can probably do this. So what I did was, I just opened the socket and then I pushed a few bytes down it and Cassandra responded and I was like, yay, something's working. But what does this mean? And sort of this talk is not so much about my driver or how to use Cassandra from Ruby, but more about sort of my experience getting over this intimidation of writing something that would just pack bytes and send them off to some magical machine in the other end of the data center and get other bytes back. And it's also going to be a lot about the CQL protocol. And I'm going to show you quite a lot of hex dumps like this, and it's not to intimidate you. I'm showing them because I want to show you how you can actually understand this. I was a bit intimidated by this, and I hope that when you leave here today that you will feel like, well, this is no problem. I can actually look at the bits and bytes going back and forth between my application and Cassandra, and I can look at that and actually see what it means. So that's sort of my aim, and I hope I'll manage. So let's dive into these bytes. The first few bits of each message. So the one on the top was what I sent to Cassandra, and the one on the bottom is what Cassandra sent me back. So those are called frames or message frames. They have a header and they have a body. And the first part of every request that you send to Cassandra will be 4 zeros. And that tells Cassandra, well, this is a this is a request, and every response you get back from Cassandra will start with a 1 followed by 3 zeros, and that tells you this is a response frame. Next, so that's the sort of expanded bit pattern of those. So next up is the version number. So the next 4 bits are the version number of the protocol. Now, there's lots of version numbers going on here because the protocol has a version number, CQL itself has a version number, and then Cassandra has a version number. And you can talk version 1 of the CQL protocol using CQL version 3.0.3 with Cassandra 2.0, or you can talk version 2 of the protocol with Cassandra 2.0 using CQL 3.0.0. So this is just the version number of the actual protocol specifying how will this message, how should you interpret this message. It has really nothing to do with CQL or with Cassandra. So many versions of Cassandra can support many versions of the protocol and vice versa. But I haven't really had the time to implement version 2 of the protocol, so this is mostly going to be a version 1. They're not very, very different. So the second byte of a message is a flags field. So it can contain a few flags. In this case, it's 0, so there's no flags set, but it could contain a flag for compression. Is this message compressed? And it can contain a flag saying, well, I want tracing on this request. So if you remember this morning, Jonathan showed you tracing in Cassandra, and that's what the driver does when you request tracing is basically just sets a bit in this field in the CQL frame header. Next up is the stream ID. So this can basically be any number between 0 and 128. And the nifty thing about this field is that Cassandra will respond with, in the response it will have the same number, so you can sort of send off a request with that number set, and you will know that when you get another response back, it will have that same number, so you can sort of pair requests and responses together. Then comes the opcode that tells Cassandra or the client what kind of a message is this really. In this case, number 1 means startup, and number 2, as is in the response, that's the ready message. And that's really important for knowing how to interpret the message body, because there's no self-description in the message bodies. You need to refer back to the protocol specification to know what how the body should be interpreted, and that's sort of where this field is absolutely crucial to figuring out the rest of the bytes. The header ends with 4 bytes. That's just the size of the body. So the header is a fixed length of 8 bytes that you can implement. When you implement a driver, you can basically just wait for 8 bytes, and you know that you will always get a response will always be at least 8 bytes, and request will always be at least 8 bytes. And then you can look at the last 4 bytes of that to know how many more bytes to expect. So in this case, the request is 22 bytes long, and the response is 0 bytes. So the ready message doesn't have a body, it's just 0. And this is then, of course, the body, variable length, as I mentioned. And for startup messages, they contain, according to the specification, a map of options. And the map in the CQL protocol is defined as 2 bytes that tell us how many entries are in this map. And in this case, the first 2 bytes are 1, so we know that there's 1 entry in this map. And then we also know from the specification that the entries will be strings. So there will be a key that's a string and the value, which is a string. And strings, I think in this case short strings to be exact, also have a prefix of 2 bytes telling us how long they are. So in this case, we have 11 bytes. The key will be 11 bytes long. these bytes, which if we look at them as ASCII are CQL underscore version. So the option in this case is CQL version. And the value for this key is 5 bytes long, these bytes, and those are, just spell out the version number that we want. So it's actually almost human parsable. It's not, I mean, it's not something you just look at it and you immediately see what it is, but that's basically it from the, that's how the protocol works. So if you ever see this in sort of, if you're sniffing your network traffic and see this, then you know what it means. But looking at it in another way, just more like a sequence diagram, this is basically what just happened. We sent Cassandra a startup message, and then we got a ready message back. Very, very simple handshake of open a connection, open your socket, push some bytes down, get a response back, make sure that it's the ready message, and then you're sort of good to go. And in another way, you push a startup message with a map of options that you want to specify for this connection. And basically, these options are more or less, you just specify the version of CQL you want and optionally what compression that you will use in subsequent messages. And compression is is a very neat feature of the protocol, which I haven't had time to implement in my driver, but that's also just, you need to tell Cassandra what kind of compression you want to use, and then just set a bit to tell it that you're using compression. So that's pretty simple to do. But sometimes now when there's a few versions of Cassandra that use the native protocol, you might need to know what options are actually possible before you start the connection. And then you can send an options message, which will be, Cassandra will respond to with the supported message. And the supported message is basically more or less the same thing as you send in the startup message. It's a map of a multi-map, it's called in the protocol specification. It's string keys, and then there's a list of strings that sort of the options that you can choose from. So it basically is the CQL version and the compression algorithms that are available. And then you send your regular startup message using one of these options, and you get ready back. Unless you're using authentication, because then it gets a bit more involved, and you might get an authenticate message back from Cassandra when you've sent your startup message. And in that case, you just formulate your credentials, your username and password, and send those to Cassandra, and then you will get a ready message back, and you know that the handshake has worked, and you're sort of authenticated to use the database. In version 2 of the protocol, that has changed slightly. There's more options to authentication, as Jonathan mentioned this morning, but essentially it works the same. So when you've gone through this handshaking, you want to sort of get down to business and actually send queries, because that's what your application is going to do. The startup phase and the handshaking is just a very, very short duration at the start of your application. Queries is sort of what it's doing the rest of the time. And that's also just one message you send to Cassandra, and you get another a response back. And the response in this case is called result. Result is a very, probably the most complex message type in the whole protocol. It's got quite a few different subtypes, and the structure of it is pretty big. It kind of looked like this. More hex dumps of CQL frames. But as before, we know this format now. We can see that this is the header of the request. We know that this is a request because it starts with 4 zeros. We know that it's the version 1 of the protocol. And then we can see that this is opcode number 7. So in this case, a query message. So we know from the specification what to expect from this, which is a long string of which is the CQL that we want to prepare. And the long string in this case just means that it's a string prefixed with the length of the string. So as you see, this one is, if I'm counting correctly, 19 characters long, which is what the 1-3 in hexadecimal just before the string means. And then there's the consistency of the request. So we want to specify which consistency that we want for this request. In this case, the consistency number 4, which corresponds to quorum. The consistencies are very easily laid out, but so 1 means 1, or rather 0 means any, 1 means 1, 2 means 2, 3 means 3, 4 means quorum, and so on up to all through, what is it, each quorum and local quorum. And then we get a response back, which is opcode 8, the response type. As I mentioned, it's got lots of subtypes. This is subtype number 2. And subtype number 2 means we can expect a metadata block and a rows block. So basically, this is when you get rows back from the database. This is how it looks. But the metadata block at the top is really important, because that's how Cassandra tells your driver or your client what kind of data it will expect. What data types are these are the columns that are returned. In this case, we have 3 columns that are going to be returned, as we can see in the highlighted number field there, and the fields are username, email, and password. And their data types come just after the names. It's just 2 bytes of types. The OD type, that's, what is it, 14 in hex? That means a string, or the text type in CQL. So this actually corresponds directly to text or varchar in the CQL language. And the last field there has the type 3, which is a blob type. So that corresponds directly to blob in when you create your table, you specify blob, and that's basically what gets sent to, that has Cassandra interprets that. Then we get the rows back. In this case, we can see that there's 2 rows, and we can see the contents of those rows here. There's actually the blob field here is, I didn't convert that to ASCII because that would probably just be unreadable. But that's sort of how it's just there as bytes. Blobs are bytes, obviously, so that's how Cassandra sends them. Most of the time you will get responses like this back, but obviously you have to expect failure at every possibility. So most of the messages that you send to Cassandra, you can always get an error frame back. That can be quite a few different kinds of error. It can be anything from the CQL that you sent is bad to I couldn't reach the desired consistency, or there's been some other kind of error inside of Cassandra that Cassandra is telling you, I can't fulfill this query, you'll have to try again or fix your query. And this could be returned when you authenticate. This can be returned when you send a query. It can be returned basically anytime. So if you write a driver, this is sort of, you need to check for errors, obviously, and you need to check for errors coming from Cassandra telling you that something has gone wrong with this query. One of the best features in my mind about the CQL protocol is the prepared statements. I like prepared statements even in relational databases. They're a great feature. They're a great feature mostly to avoid like SQL injection attacks and that kind of thing. In CQL, I'm not even sure if it's possible to do a CQL injection attack. I don't think it's legal to send more than one CQL statement in a message. but they're great for performance, and they're just great for just sending the bytes, the data over, and not sending all the CQL. You don't have to smash strings together to create a query. You just pass on the data and let the driver encode the data in as the appropriate data types. And prepared statements, they work basically like queries, but you need to do an extra round trip. You need to prepare the statement the first time you want to use it, and when you do that, you get a result frame back. The result frame in this case is another subtype of the result. So this is basically the same frame type as when you do a query, but it's got completely, mostly completely different content. But once you've done that, you can send an execute message and just specify the ID that you got back in your result frame, and the parameters to the statement instead. So let's look at how that looks as a hex dump. We can see that this is opcode number 9, so we have to refer back to the SQL protocol specification to see what's the structure of message number 9. It's a long string, which is the CQL statement that you want to prepare, and that's it. And then you get back opcode number 8 that we saw before, the result frame, but in this case, this subtype 4. So I think there's in total 6 subtypes, or maybe 5 subtypes of the result message. It's quite an overloaded message. But in this case, the first part of the first part is actually the statement ID. So this is the ID of the statement that when you want to execute this again, you need to send this ID to Cassandra, and then it knows sort of which CQL prepared statement that you meant. But the rest of the frame is actually the same as in the previous result frame that we looked at. It's a metadata block about this query. So it tells us what are the names of the columns that we prepared and what is the type. Because if you think about that, why would we need the name of the column back? If you're writing a CQL driver, you actually shouldn't try to parse the CQL. That's sort of the job of Cassandra. So when you prepare a statement, you're basically sending it in an opaque string to Cassandra. You have no idea what the structure of that string is. So you don't know which fields are bound in the statement. You need to get that data back. So Cassandra tells you that in this case, it's the username field that was prepared, and we know then that this is sort of what to expect when we execute this statement. In future, we can expect one parameter, and also it tells us what type it is, and the D type was string, or text in CQL. So some of you might already have figured this out, but I mentioned this stream ID field in the header, and that you could set that to any number between 0 and 128. And what this means is that you can have 128 requests active at any one time over a single connection. So if you want to do multiple connections in parallel, you don't need to open a new connection for every request that you want to do, or for every request in parallel that you want to do. You can actually have 128 going on at the same time per connection. So if you have a cluster of 4 nodes, for example, and you have a connection open to each of them, you can have over 500 connections going on at the same time. So the amount of parallelism just from those 4 connections is quite big. And this plays really well with like asynchronous I/O and that kind of thing. So you can have a single I/O thread that basically pushes all of the I/O, and you can multiplex this over very few connections. Yeah.
Has anybody seen in practice whether that actually has a performance benefit or not?
You mean the difference between having like 128?
TCP connection versus just like
I guess that just for low numbers, then there wouldn't probably not be that much difference, depending on, I mean, it depends on what, how you implement the I/O, obviously. But with something like NetE or just doing asynchronous I/O, having an I/O reactor doing all that, I guess that for low numbers, that wouldn't really matter. For larger numbers, maybe it could be the overhead of just having to switch between that many connections might be. But on the other hand, I mean, servers like Nginx and other high-performance I/O implementations, they do tens of thousands of connections so.
I was just wondering whether in your travels with CQL you've ever come across an instance where in practice you've seen the difference between the two.
No, I couldn't really answer the question truthfully, because I haven't implemented for example a driver for the old Thrift API where that would sort of been the what you would have to do. But either way, it's a very convenient way of just not having to keep many connections open. So it's just a nice feature of the protocol. And sort of it's 1 byte of extra data. If I'd designed it, I would have probably put 2 bytes for that, so I can have a little bit bigger windows than 128, just because it's so convenient to just have a single connection. But so getting back to so that's 1 byte of stream IDs. You can use all of the positive numbers. The negative numbers are reserved, and there's one special. The only negative numbers actually used is -1, which is server-side events. So you can register to receive events from Cassandra when things like schema changes happen or when the topology changes. So you can actually register to get notified when there's a new node joining the cluster, for example, or if a node that has failed comes back again. So that's a very convenient way of sort of discovering when you should connect to new nodes and that kind of thing. So enough about the protocol itself. I would say that implementing a CQL driver, the hard part is not actually implementing the protocol. The protocol specifications are really well written and quite easy to get your head around. You can start playing, just open a socket, as I said, and try out a few things in your terminal. You can even do it with Netcat, for example, if you're really brave. So the hard part is more in the other aspects of building a driver, and especially you need to understand that the driver and the whole application is a part of the distributed system. So it doesn't really, if you're using a highly available database like Cassandra, what's the point if your application blows up as soon as there's a problem with the network, or when you get a network partition, or when one Cassandra node goes down? So I actually did this sort of wrong from the beginning. I thought, well, I can fix that later. I just want to release version 1 and have a driver that implements the full protocol so that I can start using it and testing it out. And I thought that other things would sort of be more important. So version 1 of my Ruby driver actually, it would crash when Cassandra, if a Cassandra node went down. It would say, well, the connection closed, so I'm going to close all the connections and just stop. And I mean, why do that that just makes using Cassandra into a pretty much worse experience, just a worse experience than it could be. And you need to think like Cassandra does. You need to think about network partitions, nodes going down, that kind of thing. So in the latest version of my driver, there's lots and lots and lots of code, and probably the hardest code I've ever written that deals with this, keeping track of which connections have failed, what other nodes are in the cluster, when new nodes join the cluster, when nodes come back again from after having restarted, for example, keeping track of to connect to those again, to make sure that I fail the right requests when a connection fails. So if the request has already been sent, then obviously that request needs to be failed so that the client can be told to maybe try the request again, or maybe not try it. By the way, don't implement a thing like automatic retries of requests. That can be very convenient in some cases, but they can be disastrous in other cases. So, for example, if your client is doing increment operations and one of these increment operations fails, you don't want to automatically retry that, because even though the request, the connection, for example, might go down, but just after you send the request, but the request can still have ended up in Cassandra, so the increment had already happened. You don't want to retry that. But many operations are idempotent. It's fine to retry those, but that's not something that a driver can know. So you need to defer that to sort of the client code to decide when a retry is actually something you can do or not. Another really difficult part of writing a driver is that you get really weird bug reports that are hard to reproduce. So what looks like a white line there is actually a discussion around a GitHub issue. It went on for quite a while, and it centered around there was a guy who had this weird thing going on when he used. And don't do this at home, but he used maps for wide rows. So he basically had a single column in his table, which was a map, and then he just appended to that map and sort of tried to use that as wide rows. And then he started getting sort of random, what he felt were random results back, and we tried back and forth, and he wasn't very forthcoming in giving me example code so that I could replicate it. That's sort of why the conversation is so long. But eventually I figured out that what was going on, because I looked at the sort of just the bytes coming back from Cassandra, and so all of the data is here. So obviously it must be my driver that's doing something wrong. And I dug through my code and couldn't find anything, and eventually I went back to the specification, and then it dawned on me, well, a map in CQL is actually in the protocol, not in Cassandra, not in the storage model, but in the protocol that's actually prefixed with 2 bytes telling us how many entries will be in the map. So when you build a map over time that's more than 65,536 entries, well, you will get all the data back, but the actual number that your driver will find will be kind of, well, not random, but at least appear random, because you will get sort of the overflow. So if you have 70,000 entries in your map, your driver will actually see just the 75,000 minus 65,536 first of them. So you will see the first ones because the counter has just overflowed, and it now says that, well, there's around 445 or some entries instead of 70,000. And is this a bug in the protocol? Is this a bug in Cassandra? Is this the way it's supposed to work? Why isn't the size of maps a full int when many other fields are actually prefixed, have size prefixes that is a full int? I don't know, but these kinds of weird things crop up all of the time, and you never know when it's. Most of the time it's your fault because you're the driver implementer. So I mean, it's more likely that your code is wrong than Cassandra is wrong. But some of the times there's really weird edge cases in Cassandra that you weren't really prepared for. The final thing I want to mention, just when the difficulty of writing a driver, is just performance. Performance is always really, really important. And I guess a few of you think now, well, he's writing a driver in Ruby. How much performance can he expect? But that's true, and it will never be as performant as a Java driver, for example. But we have production systems running tens of thousands of operations per second in Ruby. So I think that the performance is pretty good. But it wasn't from the beginning, and there's not much in Ruby that helps you building a high-performance database driver. You basically have to implement things like byte buffers and that kind of thing yourself. And what you really need to avoid in a language like Ruby, you need to avoid using strings or arrays as buffers, because it's like Cassandra's wide rows. If you just append to the end and delete from the beginning, eventually the Ruby or Cassandra will sort of need to keep track of basically all of that, even though from your point of view you've deleted most of the data. There's still sort of a lot of it that needs to be kept track of. So I hope I haven't really scared you away from writing a Cassandra driver by showing you these hex dumps. I really wanted just to show you that you can actually decrypt those. Now, from having worked on writing a driver for the better part of 10 months, I can sort of decrypt those in my head. Not all of them. I can't say that I have the full specification in my head, but I sort of recognize the patterns and recognize a few of them. And sometimes that's a great debugging feature. You can actually just see what's going on and sort of debug what's happening by looking at the raw bytes going back and forth. And sort of take the leap that I did in January and try writing your own driver. You don't have to aim for doing sort of writing a driver that will be used by people. You can actually just do it out of curiosity or just for learning how Cassandra works underneath or how a protocol works underneath. I think it's been, for me, a really great experience. And this is then just the link to the actual driver that I've been working on. It's just called CQL and version 1.1 release candidate 0 was released just 37 minutes ago. That should be stable enough for production. We use it in production. It does most of the version 1 of the version 1 of the protocol. And if you're using Ruby, then I encourage you to have a look at it. So thanks. Do we have any Ruby developers here, by the way? Almost. At least one, two, and half. Oh, that's good. Oh, and one there as well. Cool. Oh, half as well. So any questions? I think we've got a few minutes for questions. Yeah?
So, do you know anything about the server side? Like on the server side, what state does it maintain about the connection? The reason why I'm asking this is what is it in the actual interaction from high level that prevents that protocol from being connected?
I think I'm the wrong person to answer that question. I guess that Michael or Sylvain would be two people to talk to. Michael is just behind you, so ask him afterwards and maybe he can point you in the right direction. Sorry. So any other questions? That? Yeah.
Does your driver actually have to care about what the application of which version of CQL, which features it's trying to use? Does that apply to the driver, or is the driver just pumping data back and forth?
Yeah, for the driver it doesn't really matter, but it's more it's a hint to Cassandra what to expect. So you're telling Cassandra, I will use this this version of the CQL, but no, the driver will never sort of inspect the CQL strings, and it shouldn't really try to do that. So I guess it will become more important when. If there's ever a CQL version 4, then it might get more important, possibly even for the driver to sort of know what to expect back from Cassandra, I guess. Not so much what the client will send, but what to expect back from Cassandra. It could be something along those lines in the future, but right now it's basically just a hint, I'd say.
So it's more parameter that driver gets from the application.
Yeah. 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 That's definitely more what it is. Yeah.
How hard did you find to test it? Did you sub out Cassandra so you could do all the error scenarios, all the error messages coming back?
Yeah. So in the beginning, I was basically developing straight against Cassandra just to get sort of valid responses back, to be able to know what sort of, because I started off trying to just from the specification write a valid response and then sort of assert that I passed that correctly, but that wasn't, I mean, I made too many mistakes that way. So I basically set up integration tests that talked to Cassandra, sent what I knew was a valid request, and then I made sure that the responses were passed correctly, and I can sort of assert on that. So the hardest parts of testing a driver in my experience is, at least, is testing the I/O stuff. You can test those at a high level and just throw requests at Cassandra and see what comes back. But if you want to throw in like what happens in error scenarios, then that's much harder. And just, I mean, in this case, it's got an I/O reactor that's doing all of the I/O and keeping track of all the connections to all different nodes. Just testing that is just very hard. I haven't got any good tools to do that. Okay, I think you had your hand up earlier, so please.
I'd like to know, do you think we would need to build our own CQL driver? I'm working with a data warehouse in the company, and currently we are extracting approximately 100 million rows from Cassandra, but through a file, and we would rather like to connect directly actually and look at our own data. Can we use Java drivers that exist with our ETL tools, or do we have to write our own?
So, sorry, you sound Norwegian. Do you work for Finn?
Yes.
Oh, very good. Well, we should talk later. You're actually one of our biggest customers. Oh, you know. Your colleagues didn't know yesterday. Great. I guess you could use the Java driver. That would probably be more performant. You shouldn't use my Ruby driver for that kind of thing, I think, because you're not a Ruby shop, and the Java driver will always be more performant. But I know that Netflix, they use in some of their analytical jobs that they're running in Hadoop, what they're doing is actually they take the raw SS tables, load those into Hadoop, and do query, or sort of do the extraction directly from the SS tables. So if you want to do massive ETL, I haven't tried this, but I've heard that that's sort of the most highly performant way of doing it. And maybe there's someone else who has experience. I saw a few nods when I mentioned this, so maybe there's someone else who has experience doing that. I don't know if there's if Cassandra itself contains a usable SS table reader. That would be awesome for you. But otherwise, I know Netflix has talked about this and they've written about this. So I would think that they have released something that can sort of at least get you started doing that. Yeah, and you should apparently talk to the guy next to Mikael. So yeah, question here.
Yes, about tests. To understand the complexity to write a driver, can you give us a rough idea how many scenario, well, your regression test, how big it is? And then you mentioned also that the most complicated part was when you had to care about cluster when a node go down and come back.
Yeah.
How easy is to automate these scenarios?
Yeah. So the driver is roughly 3,000 lines of Ruby. The tests are closer to 7,000 lines. A lot of that, would also be sort of set up for the tests and just byte dumps of sort of, this is a frame, let's pass it. But I've tried to do, so I've tried to write some, so do you know about CCM, the Cassandra Cluster Manager tool? It lets you spin up a local cluster of as many nodes as you want. It's very convenient for doing that kind of testing and stop nodes. So I've tried to sort of instrument that and run my driver and have sort of instrument the cluster taking nodes down. I wouldn't say that that's a very reliable way of testing, and sort of that says more about my lack of experience doing it than it being a valid testing strategy. But I would love to do more around that, trying to do like automate that kind of thing, automate the testing of failures. So that would be, if anyone has experience doing that, I'd love to talk to you. So there was one more question, I think. Yeah.
When you said you were then the latest version is dynamically looking at the Cassandra cluster information, like which node is down and up, does CQL provide any way to register to the gossiping, or is it completely like you're periodically pinging or?
Very good question. This was one of the things that I had no idea before I wrote this driver, and I was really, really happy to find. There is, there is a system key space. It contains, for example, it contains the schema information about which key spaces and which tables that exist, but it also contains a table called peers that has basically is a short version of the gossip information about the cluster. So you can actually query that key space to discover what other nodes are in the cluster. And that is how I do peer discovery. So when my driver connects, it connects to the nodes that the client specifies, and then it does a peer discovery by looking at that table, comparing that to the nodes it's already connected to, and then it connects to the rest of them. And that also contains like which data center it's in and that kind of thing. So you can optionally connect only to the nodes in the local data center or nodes in both data centers and that kind of thing. So I guess we're out of time, or we have one more question.
It was more of an addition to
Okay,
your
yeah,
invite. There
go
is
ahead.
also the notification API that will tell you the changes in topology of the class. Using these two mechanisms, the tables and the notification, you should be able to do less pinging and more listen.
This notification we can configure what exactly we are looking for, or is it like everybody changes the schema and the gossiping, or just?
It's more about cluster topology than changes in schemas.
There are a few different event types, and you can register for the different. So you can actually register for topology changes only, and then you get up events and down events. So and in that event, it also says which node came up and which node came down.
Actually, if so, why you did not go for that? Why you use the more hacking way of actually looking at the system key space? Why did you not go for that?
Oh, so I'm actually using both of them, but the notifications are good for knowing when things change, but you need the system key space to know how it is when things are stable. So the first thing you do is just check what's the cluster topology now, and then you listen for the events to know when things change. And I don't use I use the event more as a notification that something has changed. I don't look into the event. I found that it was just as easy just doing a new peer discovery when I get an up event. So I get an up event and I treat it like something came up, and then I just check, well, at this moment, what are the nodes? And that sort of covers if I've missed something in previously, or if I missed getting an event, then I'll pick up all of the nodes anyway. Annoyingly, the up event actually comes slightly before the node will accept connections. So sometimes you need to try again. Just slightly after you try to connect and you get an error back, and you need to try to connect again. So now I'm definitely over time, so thank you very much.